the quiet remains of a massive star. In the vast silence of space, not every ending is violent. Some are quiet, compressed into something so small and dense that its presence is almost impossible to imagine. Neutron stars are not explosions. They are what remains after one. They are the stillness left behind when a massive star has exhausted every option it had to resist gravity. What survives is not light, not heat, not brilliance, but matter pushed to its absolute limit. For most of a star's life, balance defines its existence. Gravity pulls inward, trying to crush the star under its own weight, while nuclear fusion in the core pushes outward, releasing energy that holds the star open. This balance can last millions or even billions of years, depending on the star's mass. To an outside observer, a star seems constant and eternal. But this balance is temporary. It is borrowed time. Massive stars live fast lives. They burn through their nuclear fuel quickly, fusing lighter elements into heavier ones in their cores. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen, neon, silicon, and eventually iron. Each stage produces less energy than the one before, and iron marks the end. Iron cannot release energy through fusion. Once a star's core becomes iron, the outward pressure that once held gravity at bay begins to fade. At that moment, gravity takes control completely. The core collapses. In a fraction of a second, matter falls inward at unimaginable speed. Electrons are forced into protons, merging into neutrons. The atomic structure that defines ordinary matter simply gives up. What was once a vast stellar core collapses into something far smaller, a far denser, and far stranger. The outer layers of the star rebound violently, producing a supernova, one of the most powerful explosions in the universe. But the neutron star is not the explosion. It is what remains after the noise fades. When the light of the supernova finally dissipates, the universe is left with a remnant that barely emits light at all. A neutron star does not shine like a star. It does not burn fuel. It does not glow steadily in visible light. It exists quietly, radiating faint energy across radio waves, X-rays, or gamma rays, depending on its behavior. In many cases, it is completely invisible unless its presence is inferred through indirect signals. This contrast is one of the most striking things about neutron stars. They are born from one of the brightest events in the cosmos, yet they spend the rest of their existence in near darkness. The universe trades brilliance for density, spectacle for extremity. A neutron star contains more mass than the sun, compressed into a sphere roughly the size of a city. This is not a metaphor meant to exaggerate. It is a literal description. If the sun were replaced by a neutron star, its mass would remain nearly the same, but its diameter would shrink to a few tens of kilometers. Gravity at its surface would become so intense that nothing familiar could survive there. Not rock, not atoms, not even conventional physics as we understand it. Yet neutron stars are not black holes. They represent a boundary, a stopping point where collapse halts just before space-time itself gives way. Something pushes back against gravity at the final moment, and that something is the pressure created by neutrons themselves, packed together so tightly that quantum mechanics intervenes. This resistance prevents total collapse, allowing the neutron star to exist as a stable, though extreme, object. This balance is delicate. Neutron stars exist on a knife's edge between survival and destruction. Add a little more mass, and gravity wins completely. The neutron star collapses further and becomes a black hole. Remove a little mass, and the object would not exist at all. It would have remained a white dwarf or dissipated entirely. Neutron stars occupy a narrow range in the universe. rare outcomes of specific conditions. Their rarity adds to their mystery. In a galaxy with hundreds of billions of stars, neutron stars are relatively uncommon. They form only from stars massive enough to collapse, but not massive enough to become black holes. This narrow window ensures that neutron stars are scattered sparsely across the cosmos, often isolated, often unseen. Despite their small size, neutron stars influence their surroundings profoundly. Their gravity can tear material from nearby stars. Their magnetic fields can dominate regions of space far larger than the star itself. Their rotation can generate beams of radiation so precise that they rival atomic clocks. These effects emerge not from activity in the usual sense, but from sheer extremity. The story of a neutron star begins not with violence, but with inevitability. Once fusion ends, there is no path back. Gravity does not negotiate. It compresses matter until resistance appears, or until collapse continues without limit. Where neutron stars are the universe's demonstration of how far matter can be pushed before something fundamentally different takes over. What makes neutron stars especially compelling is that they challenge intuition at every level. They are small but massive, invisible yet powerful, quiet but capable of influencing entire regions of space. They exist where familiar categories break down. Not stars, not planets, not black holes. Something else entirely. In the early days of astronomy, neutron stars were not predicted in detail. They emerged from theory as mathematical possibilities, solutions to equations that described what might happen when matter collapsed under extreme gravity. For decades, they remained hypothetical. It was difficult to imagine such objects existing in reality. The idea of matter compressed beyond atomic structure seemed more like abstraction than astrophysical fact. That changed when astronomers began detecting strange, repeating signals from space. These signals were extraordinarily regular, pulsing with precise intervals. At first, they were a mystery. Some even joked that they might be artificial in origin. But as understanding grew, it became clear that these signals were the rotational signatures of neutron stars. The universe had revealed one of its most extreme objects, not through light, but through rhythm. This discovery marked a turning point. Neutron stars were no longer theoretical remnants hidden in equations. They were real, measurable, and abundant enough to study. Yet studying them did not make them easier to understand. Each observation raised new questions. How could matter behave this way? How could such small objects exert such influence? How could they remain stable at densities that defy imagination? Neutron stars also force a reconsideration of scale. Human intuition is shaped by everyday experience. Gravity that pulls objects gently downward. Materials that behave predictably under pressure. Neutron stars exist far outside this experience. On a neutron star, a mountain would collapse under its own weight. A teaspoon of matter would outweigh entire cities. Time itself would behave differently near the surface. And yet, neutron stars are not exotic anomalies confined to theoretical corners of physics. They are natural outcomes of stellar evolution. They form according to the same laws that govern all matter and energy. They are not violations of physics, no, but confirmations of it. Proof that the equations describing gravity, quantum mechanics, and nuclear forces apply even in the most extreme conditions. This is why neutron stars are often described as cosmic laboratories. They allow scientists to observe states of matter that cannot be created on Earth. No experiment, no machine, no collider can reproduce the pressures and densities found inside a neutron star. The universe performs these experiments naturally, and astronomers observe the results from a distance. But observation comes with limits. Neutron stars are small, distant, and often obscured by dust or gas. Many emit little radiation. Others beam energy in narrow directions that may never intersect with Earth. Entire populations of neutron stars likely exist unseen, silent, and undetected, on what we know comes from a fraction of what exists. This partial view adds to their quiet presence in the universe. Neutron stars do not announce themselves loudly. They wait to be discovered, often revealing their existence only through subtle effects on nearby matter or space-time itself. In this way, they embody a recurring theme in astrophysics. The most extreme phenomena are often the least obvious. As this documentary unfolds, each layer of the neutron star will be explored, its formation, its structure, its behavior, and its role in shaping the universe. But it begins here, at the moment when a massive star ends not in disappearance, but in transformation. When light fades, gravity settles, and matter enters a state from which it will never return. The neutron star is not an ending. It is a remainder. A quiet, a compact answer to a star's final question. How much can matter endure? When gravity wins completely. Gravity is the quiet architect of the universe. It does not rush, it does not announce itself, and it does not need permission. From the formation of galaxies to the collapse of stars, gravity works patiently, pulling matter together over immense spans of time. For most stars, gravity is held in check. Nuclear fusion in the core pushes outward, creating a balance that allows the star to shine. But this balance is temporary. In the life of a massive star, there comes a moment when gravity is no longer opposed. When that moment arrives, gravity does not merely win. It overwhelms everything. To understand neutron stars, it is necessary to understand this victory of gravity, not as an abstract force, but as a physical reality that reshapes matter itself. Gravity is often perceived as weak because its effects on human scales are subtle. We feel it as weight, as a gentle pull toward the ground. But gravity is cumulative. The more mass there is, the stronger its pull becomes. In stars many times the mass of the sun, gravity becomes relentless. As a massive star exhausts its nuclear fuel, the outward pressure that once supported it begins to fade. Fusion slows, energy output drops. Gravity, which never stopped pulling inward, now encounters less resistance. The star's core begins to contract. At first, this contraction is gradual. Then it accelerates. Temperatures rise, densities increase. The core shrinks under its own weight. For a time, new forms of pressure arise to resist collapse. Electron degeneracy pressure, a quantum mechanical effect, temporarily halts contraction in less massive stars, leading to white dwarfs. But in massive stars, even this resistance fails. Gravity pushes harder. Electrons are forced into protons. The distinction between particles that once defined ordinary matter begins to dissolve. This moment marks a profound transformation. Atoms, which are mostly empty space, cannot survive the pressure. Their internal structure collapses. Protons and electrons merge, producing neutrons and releasing neutrinos in enormous quantities. The core becomes a sea of neutrons, packed together so tightly that individual atomic identities no longer matter. Matter has crossed a threshold into a new state. This is the point where gravity appears unstoppable. The core collapses inward at a significant fraction of the speed of light. In less than a second, a region larger than Earth compresses into a sphere only a few tens of kilometers across. Gravity has won not just against fusion, but against the very structure of matter. Yet the collapse does not continue forever. Something halts it. At the final moment, a new kind of resistance emerges. Neutron degeneracy pressure, combined with strong nuclear forces between neutrons, creates a counterforce powerful enough to resist further compression. Gravity and quantum mechanics reach a tense standoff. The result is a neutron star. This balance is unlike anything found elsewhere in the universe. It is not sustained by energy production as stars are. It is sustained by the fundamental rules governing particles. Neutron stars exist because quantum mechanics refuses to allow neutrons to occupy the same state indefinitely. And this refusal manifests as pressure, and that pressure is strong enough, just barely, to counter gravity. The word barely is important. Neutron stars are stable only within a narrow range of mass. If the collapsing core is too light, it will not compress enough to form a neutron star. If it is too heavy, even neutron degeneracy pressure will fail, and collapse will continue until a black hole forms. Neutron stars occupy a thin boundary between two very different cosmic outcomes. This boundary represents one of the most extreme tests of physics in the universe. Inside a neutron star, gravity is so strong that space-time itself is noticeably curved. Light leaving the surface loses energy. Time moves more slowly compared to distant observers. These effects are not theoretical curiosities, and they are measurable consequences of gravity operating at near maximum intensity. To stand on the surface of a neutron star, if such a thing were possible, would be an experience beyond comprehension. Gravity there is billions of times stronger than on Earth. A human body would be flattened instantly, stretched into a thin layer of particles. There would be no sensation, no pain, because consciousness itself could not exist under such conditions. This is gravity stripped of familiarity, gravity revealed in its purest form. Yet neutron stars are not black holes. This distinction matters deeply. In a black hole, gravity wins completely. There is no resistance. Matter collapses beyond a point where escape is possible, forming an event horizon. In a neutron star, gravity comes incredibly close to this outcome, but does not cross the final line. Something remains observable. Something remains stable. This makes neutron stars invaluable to science. They are objects where gravity is nearly as strong as it can be without destroying all structure. By studying them, scientists can observe how matter behaves under conditions approaching the ultimate limit. Neutron stars are the universe's way of showing how far gravity can go before reality changes form entirely. Gravity's victory in forming a neutron star is not loud. The supernova explosion that accompanies core collapse is spectacular, but the neutron star itself emerges quietly. Once formed, it does not expand or contract dramatically. It does not burn fuel. It simply exists, locked into an extreme state, slowly cooling over millions of years. This quiet persistence is deceptive. Though neutron stars appear inert, a gravity continues to dominate every aspect of their behavior. Their immense gravitational pull affects nearby objects profoundly. If a neutron star has a companion star, it can strip material from it, pulling gas into a swirling disk. This material accelerates, heats up, and emits powerful radiation before falling onto the neutron star's surface. Gravity transforms quiet remnants into intense cosmic engines. Even isolated neutron stars influence their surroundings. Their gravity bends space-time, affecting the paths of nearby particles and light. Their presence can be inferred through subtle distortions, timing anomalies, or gravitational interactions long before the star itself is detected. The victory of gravity in a neutron star is therefore not a single event. It is an ongoing condition. Gravity defines the star's structure, its surface, its interior, and its future. Over time, as neutron stars cool and lose energy, Gravity remains unchanged. It does not weaken. It does not forget. It waits. This waiting matters because neutron stars are not always alone. In binary systems, two neutron stars may orbit each other for millions or billions of years. Slowly, gravity draws them closer together. Energy is lost through subtle emissions, including ripples in space-time itself. Eventually, gravity completes its long campaign, and the stars collide. When that happens, gravity once again reshapes matter on a cosmic scale. The story of neutron stars is therefore inseparable from gravity's story. From their formation to their interactions and eventual fate, gravity is the central force. It is the reason neutron stars exist, and the reason they are so extreme. While what makes this story especially compelling is that gravity does not need complexity to be powerful. It follows simple rules. It pulls mass toward mass. Yet when enough mass accumulates, those simple rules produce outcomes that defy intuition. Neutron stars are among the clearest examples of this principle. Simple gravity, acting on immense mass, creates objects that challenge every assumption about matter and space. A star, crushed into a city size, is one of the most deceptive concepts in astronomy. The universe is filled with objects so large that they overwhelm human imagination. Yet neutron stars challenge perception in the opposite direction. They are not vast. They are not expansive. They are small, shockingly small, especially when compared to what they once were. A neutron star is the remnant of a massive star that may have been millions of kilometers across, reduced to a sphere barely larger than a city. This transformation defies intuition. When people imagine powerful cosmic objects, they often picture enormous structures stretching across space. Neutron stars contradict this expectation. Their power does not come from size, but from density. They demonstrate that in the universe, compression can be as significant as expansion. A typical neutron star measures roughly 20 kilometers in diameter. That distance could be crossed in minutes by a car traveling on Earth. Yet within that small volume lies more mass than the sun itself. To place this in perspective, imagine compressing a star containing hundreds of thousands of Earths into a space smaller than many metropolitan areas. As nothing in everyday experience prepares the mind for such concentration of matter. This density is not gradual. It is absolute. There is no hollow interior, no soft core, no layered structure like a planet's crust and mantle in familiar terms. Matter inside a neutron star is packed as tightly as the laws of physics permit without collapsing further. Each cubic centimeter contains mass comparable to a mountain. A single teaspoon of neutron star material would outweigh entire cities. The human mind struggles with this scale because density is invisible. We see size easily. We feel weight locally. But density combines mass and volume in a way that defies instinct. Neutron stars force a redefinition of what heavy means. They are heavy not because they are large, but because everything they contain has been stripped of space. Atoms, which make up all ordinary matter, are mostly empty. Their nuclei are tiny compared to the space occupied by electron clouds. In everyday objects, this emptiness goes unnoticed. But gravity inside a collapsing star does not tolerate emptiness. It compresses matter until that empty space disappears. In a neutron star, atoms cease to exist. Their components are pressed together into a nearly continuous substance. This is why the phrase, city-sized star, is so unsettling. A star is supposed to be large. It is supposed to dominate space visually. Neutron stars hide their extremity behind small dimensions. They look insignificant from afar, yet they are among the most extreme objects in existence. If Earth were replaced by a neutron star, the result would be catastrophic and immediate. Its gravity would tear apart everything nearby. The moon's orbit would collapse. Oceans would be pulled into space. The planet itself would be shredded long before any observer could fully comprehend what was happening. This is not because neutron stars are violent by nature, but because density amplifies gravity beyond anything Earth can resist. Even light behaves differently near such density. Photons climbing away from a neutron star lose energy. Their wavelengths stretch. Colors shift. Space itself is curved so strongly that paths bend noticeably. Looking at a neutron star is not like looking at a distant object. It is like peering into a region where the geometry of reality has been altered. Despite this, neutron stars do not collapse into black holes immediately. Their small size does not mean instability. On the contrary, they are remarkably stable within a narrow mass range. Their compactness is precisely what allows them to exist. The same compression that creates extreme gravity also triggers quantum effects that resist further collapse. This balance between compression and resistance is delicate. Add just a little more mass, and the neutron star would no longer be able to support itself. The city-sized remnant would shrink further, crossing the threshold into a black hole. Remove mass, and it could not have formed in the first place. Neutron stars exist at a precise intersection of forces, size, and mass. The scale of neutron stars also influences how they interact with their surroundings. Because they are so small, their gravitational field changes rapidly over short distances. Near the surface, gravity is overwhelming. Move just a few kilometers away, and the pull drops sharply. This steep gradient affects how matter behaves around them, tearing apart nearby material and shaping intense radiation environments. When gas falls toward a neutron star, it accelerates to extraordinary speeds. By the time it reaches the surface, it is moving at a significant fraction of the speed of light. The energy released in this final plunge is immense. Yet it all occurs in a region no larger than a city. Power that would require entire galaxies to produce elsewhere is concentrated into a space small enough to fit within a human landscape. This compression also affects time. Near a neutron star, time passes more slowly relative to distant observers. Clocks near the surface tick differently. This is not science fiction. It is a measurable effect predicted by general relativity and confirmed by observation. The city-sized scale of neutron stars becomes a laboratory where space and time are visibly distorted. The idea that something so small can contain such power forces a shift in perspective. In the universe, significance is not always proportional to size. Neutron stars show that extreme conditions arise when matter is forced into confinement. They are monuments to compression, reminders that the universe can concentrate its forces into surprisingly small spaces. Astronomers often describe neutron stars using comparisons because numbers alone are insufficient. They are described as having the mass of the sun, the size of a city, and the density of an atomic nucleus. Each comparison attempts to bridge the gap between human experience and cosmic reality. None fully succeeds. Even among stellar remnants, neutron stars stand apart. As white dwarfs, the remnants of smaller stars are roughly Earth-sized. They are already incredibly dense. Neutron stars compress that density further by several orders of magnitude. Black holes take the process to its ultimate conclusion. Neutron stars sit between these outcomes, representing the last stable form of matter before space-time itself gives way. This intermediate status gives neutron stars a unique role in astrophysics. They are not endpoints in the sense of stillness. They are dynamic, rotating, magnetized objects that continue to interact with their environment long after their formation. Their small size allows them to spin rapidly, often hundreds of times per second, without tearing themselves apart. This rapid rotation, combined with extreme density, gives neutron stars extraordinary angular momentum. When a massive star collapses, conservation of angular momentum causes its core to spin faster as it shrinks. The result is a city-sized object, rotating at rates that defy everyday experience. Entire stellar cores compressed into a sphere, spinning many times per second. Such rotation would destroy any ordinary object. But neutron stars are held together by gravity so intense that even these speeds are sustainable. The small size of neutron stars makes these rotations possible, further amplifying their uniqueness. The concept of a star reduced to city size is not just a curiosity. It is central to understanding how neutron stars behave, how they emit energy, and how they influence the cosmos. Their compactness is the foundation of every extreme property they possess. When scientists speak of neutron stars, they often emphasize mass and density rather than size. But it is the contrast between mass and size that makes neutron stars unforgettable. They are reminders that the universe does not conform to human expectations of scale. Enormous power can exist in the smallest of places, matter under impossible pressure. Inside a neutron star, matter no longer behaves as matter is expected to behave. The familiar rules that govern solids, liquids, and gases dissolve under pressure so extreme that even atomic structure cannot survive. This is not merely high pressure by earthly standards. It is pressure so intense that it rewrites the definition of matter itself. To understand this, it helps to remember what ordinary matter is made of. Atoms consist of a tiny nucleus surrounded by electrons occupying vast regions of empty space. In everyday objects, this emptiness goes unnoticed. A table feels solid. The ground feels firm. But at the atomic level, nearly everything is space. Neutron stars eliminate that space almost entirely. As gravity compresses a collapsing stellar core, electrons are forced closer and closer to atomic nuclei. Eventually, there is nowhere left for them to go. At this point, a dramatic transformation occurs. Electrons are pushed into protons, merging to form neutrons. This process releases neutrinos in enormous quantities, which escape into space, carrying energy away. What remains behind is matter composed almost entirely of neutrons. This state of matter is unlike anything found naturally elsewhere in the universe. It is not plasma. It is not solid or liquid in any familiar sense. It is neutron-degenerate matter, a substance supported not by heat or chemical bonds, but by the fundamental rules of quantum mechanics. Neutrons resist being compressed into the same quantum state, and this resistance creates pressure powerful enough to oppose gravity. The pressure inside a neutron star is so immense that it is difficult to describe without exaggeration. At the surface, gravity already exceeds anything imaginable. Deeper inside, pressure rises rapidly. Within just a few kilometers, it surpasses the pressure found in atomic nuclei. At these depths, matter exists in conditions that scientists cannot reproduce, simulate, or directly observe. This is where certainty fades and theory takes over. Physicists know that neutrons dominate the interior, but exactly how they arrange themselves remains an open question. Some models suggest that neutrons behave like a superfluid, flowing without friction. Others propose that exotic particles emerge, hyperons, mesons, or even free quarks, forming states of matter never seen elsewhere. These possibilities are not speculation in the casual sense. They are serious predictions based on known physics pushed to its limits. Pressure inside a neutron star increases toward the core. Near the surface, a thin crust exists, a rigid lattice of nuclei immersed in a sea of electrons. This crust is extraordinarily strong, far stronger than steel, yet even this strength is relative. Beneath the crust, matter transitions into a dense ocean of neutrons, where solidity loses meaning. The deeper one goes, the less familiar physics becomes. At these depths, temperature matters less than pressure. Neutron stars are born extremely hot, but they cool relatively quickly on cosmic timescales. Even as they cool, pressure remains dominant. The structure of the star is determined not by heat, but by the balance between gravity and quantum forces. This makes neutron stars cold in temperature, but extreme in every other sense. The concept of pressure inside a neutron star is misleading if imagined as something pressing from all directions equally. In reality, gravity creates a gradient. Pressure increases rapidly with depth. A neutron star only a few kilometers across contains layers of radically different physical regimes stacked tightly together. Each layer transitions into the next over distances smaller than cities, yet represents changes greater than anything seen across planets. This layering is one reason neutron stars are so difficult to model. Small changes in assumptions about particle interactions can lead to very different predictions about structure and stability. Scientists use observations, such as mass, radius, and rotation, to constrain these models, but uncertainty remains. The interior of a neutron star is hidden not by distance, but by physics itself. Pressure also explains why neutron stars do not collapse immediately into black holes. At the highest densities, neutron degeneracy pressure and strong nuclear forces work together to resist further compression. These forces are short-range, but extraordinarily powerful. They act at distances comparable to the size of particles themselves. Gravity, though strong, must overcome these forces to cause further collapse. This balance defines the maximum mass a neutron star can have. Above this limit, pressure can no longer resist gravity. The star collapses further, forming a black hole. Below it, neutron stars can exist stably for billions of years. Determining this limit precisely is one of the central challenges in modern astrophysics. Pressure also influences how neutron stars respond to external forces. When material falls onto a neutron star from a companion, the added mass increases pressure in the interior. If enough mass accumulates, the star may be pushed beyond its stability threshold. In this way, pressure determines not only what neutron stars are, but what they may become. Inside neutron stars, sound travels at incredible speeds. Waves propagate through matter that is nearly incompressible, and as star quakes, fractures in the crust caused by stress can release enormous amounts of energy. These events are not earthquakes in the usual sense, but adjustments within a crust stronger than anything on Earth. Pressure shapes these events, storing and releasing energy in unfamiliar ways. The inability to directly sample neutron star interiors makes pressure both a subject of fascination and frustration. No probe can survive such conditions. No signal escapes unaltered. What scientists know comes from indirect evidence: how neutron stars spin, how they wobble, how they cool, and how they respond to disturbances. Each observation narrows the range of possible interior states, but never reveals them completely. This uncertainty is not a weakness. It is a reminder that neutron stars represent the frontier of knowledge. They are places where known physics overlaps with unknown outcomes. Pressure pushes matter into regimes where theory must be tested against reality, and where even small insights can reshape understanding. Neutron stars also serve as reminders that the universe explores conditions beyond human reach. Where Earth offers gentle gravity and familiar matter, neutron stars offer compression so severe that matter itself is transformed. They are cosmic experiments running continuously, silently testing the laws of nature. The birth of a neutron star. The birth of a neutron star is one of the fastest and most decisive events in the universe. It does not unfold over years or even minutes. It happens in seconds. In that brief span, a massive star that has existed for millions of years completes its transformation into one of the densest objects known to physics. What makes this moment extraordinary is not just its violence, but its finality. Once the process begins, there is no reversal. Long before the birth of a neutron star, its parent star has already lived a complex life. Massive stars burn through their fuel rapidly, fusing elements in their cores in a precise sequence. Each fusion stage produces energy that counters gravity, allowing the star to maintain its structure. But with each heavier element produced, the energy return diminishes. Eventually, the core becomes dominated by iron. At that point, the star reaches a dead end. Iron cannot release energy through fusion. Instead of pushing outward, the core becomes a burden. Gravity, one which has been patiently waiting, seizes the opportunity. The balance that defined the star's life disappears almost instantly. The core begins to collapse inward under its own immense weight. As the core collapses, conditions change with staggering speed. Temperatures soar, densities increase rapidly. Electrons are forced into atomic nuclei, combining with protons to form neutrons. This process, known as neutronization, releases an enormous number of neutrinos. These nearly massless particles escape the collapsing core, carrying away energy and accelerating the collapse further. The collapse continues until neutron degeneracy pressure and nuclear forces intervene. At this point, the inward motion of the core halts abruptly. The outer layers of the star, still falling inward, slam into this suddenly rigid core and rebound violently. This rebound generates a shockwave that races outward, tearing the star apart in a supernova explosion. The supernova is spectacular. For a brief time, the exploding star can outshine an entire galaxy. Heavy elements forged in the star's core are scattered into space, seeding future stars and planets. But while the explosion captures attention, the neutron star itself forms quietly at the center, largely hidden from view. Within seconds of core collapse, the neutron star is born. It is already spinning rapidly, conserving angular momentum from the original star. It is already intensely magnetized, its magnetic field amplified by the compression of stellar material. It is already defined by extreme gravity and density. The transformation is complete. What makes this birth remarkable is how little time it takes compared to the star's lifespan. Millions of years of nuclear fusion end in seconds of collapse. The universe invests vast amounts of time in building massive stars, only to reshape them in an instant when gravity finally prevails. The newborn neutron star is not calm. It vibrates, it oscillates, it emits neutrinos and radiation as it settles into equilibrium. These early moments are turbulent, but brief. Very quickly, the neutron star stabilizes into a long-lasting remnant that can persist for billions of years. Not every collapsing core produces a neutron star. The outcome depends on mass. If the core is too light, it may form a white dwarf instead. If it is too heavy, neutron degeneracy pressure fails, and collapse continues until a black hole forms. See, neutron stars are born only in a narrow range of conditions, making each one a rare product of cosmic evolution. The birth environment also influences the neutron star's future. Rotation speed, magnetic field strength, and surrounding material all shape how the neutron star will behave over time. Some will become pulsars, emitting regular beams of radiation. Others will become magnetars, dominated by extreme magnetic forces. Some will remain quiet, cooling slowly in isolation. Even at birth, neutron stars demonstrate the universe's efficiency. Nothing is wasted. Energy released in the supernova drives chemical evolution across galaxies. Neutrinos carry information about the collapse across cosmic distances. The neutron star itself preserves mass and angular momentum in a compact form that influences its surroundings long after the explosion fades. The speed of neutron star formation challenges human intuition. Events of such importance are often imagined as slow and gradual. Instead, the universe compresses a massive stellar core into a city-sized object in less time than it takes to read a paragraph. Gravity does not hesitate. When conditions are right, it acts decisively. This rapid birth also makes direct observation difficult. By the time light from the supernova reaches Earth, the neutron star has already formed and stabilized. What astronomers see are after effects, indirect signals, and long-term behavior. The moment of formation itself remains largely hidden, inferred through models and fleeting neutrino detections. Despite this, the birth of neutron stars is one of the best understood processes in high-energy astrophysics. It combines gravity, nuclear physics, quantum mechanics, and relativity into a single event. Each successful observation or simulation deepens understanding of how matter behaves under extreme conditions. Neutron star births also mark continuity. The elements scattered by the supernova become part of future stars, planets, and life. The neutron star remains behind as a silent witness to that process, a reminder of the star that once was and the forces that reshaped it. The surface of a neutron star. The surface of a neutron star is not a place in the ordinary sense. It is not ground, not land, not terrain shaped by wind or erosion. It is a boundary, the final layer where matter resists gravity just enough to exist, and everything below this surface is compressed into states beyond normal experience. Everything above it is open space. And at this boundary, the laws of physics behave in ways that feel almost unfamiliar. Gravity at the surface of a neutron star is overwhelming. It is not slightly stronger than Earth's gravity. It is not even thousands of times stronger. It is billions of times stronger. Any object approaching the surface would accelerate so rapidly that it would reach a significant fraction of the speed of light before impact. There would be no gentle landing, no gradual descent. The fall would be final and instantaneous. If a human could somehow survive the journey, which is impossible, the body would not simply be crushed. It would be stretched and compressed at the same time. The difference in gravitational pull between head and feet would be so extreme that the body would be torn apart at the subatomic level. Even molecules would not remain intact. This is not danger as we understand it. It is a complete breakdown of structure. The surface itself is extraordinarily thin. Compared to the size of the neutron star, the outer crust is only a small fraction of the total radius. Yet, within this thin layer lies some of the strongest material in the universe. The crust of a neutron star is composed of tightly packed atomic nuclei, arranged in a rigid lattice, immersed in a sea of electrons. This structure gives the crust immense strength, far beyond any material found on Earth. Despite this strength, the crust is under constant stress. The neutron star's rotation, magnetic field, and internal dynamics place strain on this rigid shell. Over time, this stress can build until the crust fractures. When it does, the result is a starquake, a sudden rearrangement of matter that releases enormous amounts of energy. These events are not earthquakes in the traditional sense, but they are among the most violent surface phenomena known. The gravity at the surface affects more than just objects falling toward it. It alters how light behaves. Photons climbing away from the neutron star lose energy, becoming redshifted. Colors shift toward longer wavelengths. An observer far away sees light that has been stretched by gravity itself. This effect is one of the clearest demonstrations of general relativity in action. Space near the surface is not flat. It is curved strongly by the neutron star's mass. Paths that would be straight elsewhere bend noticeably here. Light traveling near the surface can curve around the star, making regions on the far side partially visible. In a sense, a neutron star bends the universe around itself, revealing how mass reshapes space. Time behaves differently at the surface as well. Clocks placed near a neutron star would tick more slowly than clocks far away. This is not a metaphor. It is a measurable effect. Time dilation near neutron stars has been confirmed through precise observations of pulsars and binary systems. The closer one gets to the surface, the more time itself slows. The surface temperature of a newly formed neutron star is extraordinarily high. Shortly after birth, temperatures can reach millions of degrees. Over time, the star cools by emitting radiation and neutrinos. As yet, even after millions of years, the surface remains extremely hot by everyday standards. This heat is not produced by fusion, but by residual energy from formation and internal processes. Despite this heat, neutron stars do not glow like ordinary stars. Their small surface area limits the total amount of light they emit. Many neutron stars are effectively invisible in visible light, detectable only through X-rays or radio emissions. Their presence must often be inferred rather than seen directly. Anything that falls onto a neutron star releases an immense amount of energy upon impact. Because gravity accelerates matter to such extreme speeds, the collision converts motion directly into radiation. Even small amounts of infalling material can produce powerful bursts of X-rays or gamma rays. This makes neutron stars among the most efficient energy converters in the universe. In binary systems, this process becomes dramatic. Gas drawn from a companion star forms a swirling disk around the neutron star before falling onto the surface. As it spirals inward, it heats up, glowing intensely. When it finally strikes the surface, it releases a flash of energy that can briefly outshine entire regions of space. All of this happens on a surface no larger than a city. The surface of a neutron star is also shaped by its magnetic field. Magnetic forces channel charged particles toward specific regions, often near the magnetic poles. This focused inflow creates hotspots that emit intense radiation. As the neutron star rotates, these hotspots sweep through space, producing beams that can be detected across vast distances. This interaction between gravity, magnetism, and rotation gives neutron stars their characteristic behavior. The surface is not static. It is shaped continuously by forces that operate at extremes rarely encountered elsewhere. Yet, despite this activity, the neutron star remains stable, enduring for billions of years. The idea of a surface existing under such conditions challenges intuition. On Earth, surfaces are places of interaction. Air meets land, water meets shore. On a neutron star, the surface is the final resistance against collapse. It is the last layer where matter retains any recognizable structure before entering a regime governed almost entirely by nuclear and quantum forces. Studying neutron star surfaces provides crucial insight into their internal structure. Observations of emitted radiation, temperature changes, and timing variations help scientists infer what lies beneath. Because the interior cannot be observed directly, the surface becomes a messenger, carrying subtle clues from the depths below. Yet, interpretation remains difficult. Extreme gravity alters signals before they reach observers. Magnetic fields distort emission patterns. Rotation adds complexity. Untangling these effects requires careful modeling and long-term observation. Each measurement refines understanding, but never provides a complete picture. The surface of a neutron star is therefore both a boundary and a window. It separates known physics from unknown regimes, while offering glimpses into conditions unreachable by experiment. It is a place where gravity approaches its limit without crossing into total collapse. Extreme magnetism. If gravity defines the structure of a neutron star, magnetism defines its personality. Nowhere else in the universe do magnetic fields reach such extraordinary strength. On Earth, magnetism quietly guides compasses and shields the planet from solar wind. Around neutron stars, magnetism dominates space itself, shaping matter, radiation, and motion across vast distances. A neutron star's magnetic field is not something it generates anew. It is inherited. The massive star that collapsed carried its own magnetic field, modest by cosmic standards. When the star's core collapsed into a city-sized remnant, that magnetic field was compressed along with the matter. Magnetic field lines that once spanned millions of kilometers were squeezed into a region only tens of kilometers across. The result was amplification on an unimaginable scale. The typical magnetic field of a neutron star is trillions of times stronger than Earth's. This number is difficult to grasp because magnetism is invisible. It does not have weight or texture. Yet in such strength, magnetic fields become forces that actively reshape matter. At these levels, magnetism can strip atoms apart, align particles into rigid structures, and control the motion of charged matter across space. Near a neutron star, magnetic fields dominate over almost every other influence except gravity itself. Charged particles cannot move freely. Instead, they spiral tightly along magnetic field lines, locked into invisible pathways that guide their motion. Plasma near the star behaves less like a gas and more like a constrained system, enforced into patterns dictated by magnetism. This extreme magnetism extends far beyond the neutron star's surface. Magnetic field lines stretch into space, forming vast magnetospheres that can extend thousands of kilometers. Within these regions, particles are accelerated to near-light speeds, emitting intense radiation as they move. These emissions are often the only way neutron stars reveal themselves to distant observers. The strength of a neutron star's magnetic field also influences its evolution. Over time, magnetic energy can be released, transferred, or rearranged. In some neutron stars, magnetic fields decay slowly over millions of years. In others, they remain stable, maintaining their intensity across vast spans of time. The reasons for these differences are still not fully understood. Magnetism also interacts closely with rotation. Most neutron stars rotate rapidly, and as they do, their magnetic fields sweep through space. This motion generates electric fields capable of accelerating particles to extreme energies. The combined effect of rotation and magnetism transforms neutron stars into powerful cosmic engines, converting rotational energy into radiation with remarkable efficiency. In regions near the magnetic poles, magnetic field lines open outward, allowing particles to escape. These particles emit beams of radiation that sweep across space, as the neutron star rotates. When one of these beams crosses Earth, it appears as a pulse, a brief flash of energy repeating with astonishing regularity. This phenomenon would later become one of the most important tools in astrophysics. But not all neutron stars behave the same way. Magnetic field strength varies widely. Some neutron stars possess relatively modest fields, while others are born with fields so strong that they challenge existing models of physics. These differences lead to dramatically different observational behavior, from quiet, cooling remnants to intensely active sources of radiation. Extreme magnetism also affects the neutron star's surface directly. The crust, already under immense stress from gravity and rotation, is further strained by magnetic forces. Field lines anchored in the crust resist movement. Over time, stress builds as the star cools and its internal structure shifts. When the stress becomes too great, the crust fractures, releasing magnetic energy in powerful bursts. These magnetic rearrangements do not resemble anything familiar. They are not gradual releases like solar flares. They are sudden, violent shifts that can alter the star's magnetic configuration almost instantly. The energy released in such events can exceed what the sun emits over thousands of years, concentrated into a brief flash lasting fractions of a second. The surrounding space feels the effects immediately. Radiation surges outward. Particles are accelerated violently. In some cases, these events are detectable across the entire galaxy, despite originating from an object smaller than a city. This contrast, immense energy from tiny scale, is a recurring theme in the story of neutron stars. Magnetism near neutron stars also influences how matter falls onto them. In binary systems, gas drawn from a companion star does not fall evenly across the surface. Instead, magnetic fields funnel material toward the magnetic poles, creating narrow streams of infalling matter. When these streams strike the surface, they produce intense hotspots that dominate the star's emission. This channeling effect gives neutron stars structured behavior. Their emissions are not random. They follow patterns dictated by magnetic geometry and rotation. By studying these patterns, astronomers can infer the orientation, strength, and structure of magnetic fields that cannot be seen directly. Despite decades of study, many questions about neutron star magnetism remain unanswered. How are such extreme fields generated initially? Why do some decay rapidly while others persist? How do magnetic fields interact with superdense matter in the interior? These questions lie at the frontier of astrophysics, and where theory and observation struggle to meet. What is clear is that magnetism transforms neutron stars from inert remnants into dynamic objects. Without magnetic fields, neutron stars would be far quieter, harder to detect, and less influential. Magnetism gives them voice, structure, and presence in the universe. The quiet intensity of neutron star magnetism also serves as a reminder of scale. Forces that feel gentle on Earth become dominant when concentrated into small regions with extreme density. Neutron stars reveal how fundamental interactions behave when pushed far beyond everyday limits. Magnetars. When magnetism breaks reality. Among all neutron stars, there exists a rare and unsettling class that pushes magnetism beyond anything else known in the universe. These objects are called magnetars. They are not a different kind of star in origin, but a different outcome in intensity. Where ordinary neutron stars possess magnetic fields already trillions of times stronger than Earth's, magnetars amplify that power 1,000-fold more. In these objects, magnetism becomes the dominant force shaping reality around them. A magnetar's magnetic field is so strong that it defies everyday understanding of physics. Near its surface, the field can exceed 10 to the power of 15 Gauss. At these strengths, magnetic forces rival or even surpass the forces that bind atoms together. Space around a magnetar does not behave normally. The vacuum itself becomes distorted, reacting to magnetic stress in ways predicted by quantum theory but rarely observed. The origin of magnetars lies in the earliest moments of neutron star formation, or when a massive star collapses, its core may rotate extremely rapidly, completing multiple rotations per second. This rapid rotation, combined with intense convection during collapse, can generate an extraordinarily powerful magnetic dynamo. The result is a newborn neutron star with a magnetic field far stronger than typical. Over time, this field does not simply remain passive, it becomes unstable. Unlike ordinary neutron stars, where magnetic fields gradually decay or remain relatively steady, magnetar fields twist and strain the star's crust continuously. Magnetic field lines anchored in the crust resist movement, but the internal field is restless. As the neutron star cools and contracts slightly, magnetic stresses build. The crust, though incredibly strong, cannot withstand this pressure indefinitely. When the crust fractures, the result is a starquake. But magnetar starquakes are not minor adjustments. They release immense amounts of energy stored in the magnetic field. In a fraction of a second, a magnetar can emit more energy than the sun produces over tens of thousands of years. This energy is released primarily as gamma rays and X-rays, forming intense bursts detectable across vast distances. These events are among the most powerful explosions known that do not destroy the star itself. Unlike supernovae, magnetar flares leave the star intact. The magnetar survives, altered but still present, continuing its slow evolution under magnetic stress. This ability to release enormous energy repeatedly without collapsing makes magnetars uniquely dangerous and fascinating objects. The strongest magnetar flares are so intense that they can affect regions far beyond the star itself. In rare cases, gamma-ray bursts from magnetars have been detected across the Milky Way. Some events are powerful enough to disturb Earth's upper atmosphere, despite originating tens of thousands of light years away. This demonstrates just how extreme magnetar energy release can be. Near a magnetar, the magnetic field dominates particle motion completely. Charged particles are locked into rigid paths, spiraling tightly along field lines. Atoms cannot maintain their usual shapes. Electron clouds become elongated. Chemical behavior changes. Matter becomes structured by magnetism rather than temperature or pressure. In this environment, even light behaves differently. Quantum effects become significant. Strong magnetic fields can alter how photons propagate through space, causing polarization and birefringence effects normally associated with crystals. In the vicinity of a magnetar, empty space behaves as if it were a material medium. This is not metaphorical language. It is a direct consequence of quantum electrodynamics operating under extreme conditions. Magnetars are relatively short-lived compared to other neutron stars. Their intense magnetic fields decay over tens of thousands of years, releasing energy continuously. As the field weakens, magnetar activity declines. Eventually, a magnetar may settle into a quieter neutron star state, its most violent phase behind it. This transient nature explains why magnetars are rare. They exist only briefly on cosmic timescales. Despite their rarity, the magnetars play an important role in astrophysics. They demonstrate the upper limits of magnetic field strength in the universe. They provide natural laboratories for studying quantum effects in extreme fields. They also help explain mysterious high-energy phenomena observed across the galaxy. Not all magnetar activity is catastrophic. Many emit smaller bursts repeatedly, releasing energy in controlled but powerful flashes. These bursts can be studied to infer magnetic field structure, crust strength, and internal dynamics. Each event offers a glimpse into processes occurring deep within the star. The existence of magnetars also challenges assumptions about stellar remnants. It shows that neutron stars are not uniform outcomes. Initial conditions during formation can lead to radically different evolutionary paths. Two neutron stars born from similar supernovae may diverge dramatically based on rotation speed and magnetic amplification. Magnetars highlight a recurring theme in astrophysics. Extremes often emerge from subtle differences. A slightly faster rotation, a slightly stronger initial field, and the result is an object capable of reshaping its surroundings through magnetism alone. The universe does not need exotic materials or unknown forces to produce such power. It relies on the same physics, pushed to extraordinary limits. For astronomers, magnetars are both opportunities and warnings. They reveal how energy can be stored and released under extreme conditions. They also demonstrate how close known physics comes to its boundaries. Understanding magnetars helps refine theories of matter, magnetism, and space-time itself. Yet magnetars remain unpredictable. Their bursts occur without warning. Their magnetic configurations change abruptly. Observing them requires constant monitoring and rapid response. Even with modern instruments, much of their behavior remains mysterious. Magnetars remind us that neutron stars are not static remnants. They are dynamic objects capable of dramatic transformation. Among them, magnetars represent the most intense expression of magnetism in the cosmos, where fields strong enough to reshape atoms and space itself dominate reality. Pulsars, the universe's most precise beacons. Not all neutron stars express their power through violence. Some reveal themselves through order, through rhythm, through repetition so precise that it rivals the most accurate instruments ever built by humans. These neutron stars are known as pulsars, and they transform rotation into one of the most reliable signals in the universe. Pulsars were not discovered because astronomers were searching for neutron stars. They were discovered because something in space was behaving with impossible regularity. In the late 20th century, radio telescopes detected signals that repeated at exact intervals, sometimes multiple times per second. The timing was so precise that early researchers briefly considered artificial origins. Nothing in nature was expected to behave like this. The explanation turned out to be both simple and astonishing. A pulsar is a rotating neutron star whose magnetic field channels radiation into narrow beams emitted from its magnetic poles. These beams sweep through space as the star rotates. If one of those beams crosses Earth, it appears as a pulse. The neutron star itself does not turn on and off. It spins steadily, and the pulse is a matter of geometry. This lighthouse effect gives pulsars their name. But unlike lighthouses on Earth, pulsars do not slow easily. Their rotation is maintained by immense angular momentum inherited during collapse. As the core of a massive star shrinks from thousands of kilometers to city size, rotation speeds increase dramatically. Conservation of angular momentum turns collapsing stellar cores into extraordinarily fast rotators. Some pulsars rotate several times per second. Others rotate hundreds of times per second. The fastest known pulsars spin more than 700 times per second, completing a full rotation in just milliseconds. At these speeds, the surface moves at a significant fraction of the speed of light, yet the neutron star remains intact. What makes pulsars extraordinary is not just speed, but stability. Many pulsars maintain their rotation with astonishing precision. Over years of observation, their pulse timing varies by less than a fraction of a microsecond. In some cases, pulsars rival atomic clocks in accuracy. This precision makes them invaluable tools for science. Pulsars act as cosmic timekeepers. By monitoring their pulses, astronomers can detect subtle changes in space-time. Variations in pulse timing reveal the presence of orbiting companions, distortions caused by gravitational waves, or even tiny changes in Earth's motion. Pulsars turn neutron stars into instruments that measure the universe itself. The emission from pulsars spans a wide range of wavelengths. Some are strongest in radio waves. Others emit X-rays or gamma rays. The specific emission depends on magnetic field strength, rotation rate, and surrounding environment. Yet, regardless of wavelength, the defining feature remains the same: repetition. Over time, pulsars slowly lose rotational energy. As they emit radiation and accelerate particles, they spin down gradually. This slowdown is predictable and measurable. By studying it, astronomers can estimate a pulsar's age and energy output. Even in slowing, pulsars remain remarkably stable. Occasionally, this stability is interrupted. Some pulsars experience sudden changes in rotation known as glitches. These events involve abrupt increases in spin rate, believed to result from interactions between the neutron star's crust and its superfluid interior. Glitches offer rare insight into the internal structure of neutron stars, revealing that even under extreme conditions, internal dynamics remain active. Pulsars are also found in binary systems, orbiting other stars or even other neutron stars. In these systems, pulsar timing becomes even more powerful. Orbital motion introduces regular variations in pulse arrival times, allowing astronomers to measure masses, test general relativity, and detect energy loss through gravitational radiation. Pulsars in binary systems have confirmed some of the most fundamental predictions of modern physics. One remarkable class of pulsars is known as millisecond pulsars. These objects rotate extraordinarily fast and are believed to have been recycled. Over long periods, they accreted matter from a companion star, gaining angular momentum and spinning up to extreme speeds. This process demonstrates that neutron stars are not static remnants, but evolving systems shaped by their environments. Despite their precision, pulsars are not permanent. Over millions of years, they slow enough that their emission beams weaken or no longer intersect Earth. When this happens, they fade from detection, becoming quiet neutron stars once again. Many more neutron stars exist than are observed as pulsars, hidden simply because their beams do not point toward us. This geometric limitation explains why pulsars are rare compared to the total neutron star population. Detection depends on orientation. Countless neutron stars rotate silently, their beams sweeping empty space. What we observe is a biased sample, a reminder that the universe often hides more than it reveals. Pulsars also illuminate the environments around them. Their powerful winds of charged particles create nebulae, energizing surrounding gas and dust. These pulsar wind nebulae glow across the electromagnetic spectrum, marking the presence of a neutron star long after the original supernova fades. The study of pulsars reshaped astronomy. It transformed neutron stars from theoretical curiosities into precision instruments. It demonstrated that extreme gravity and magnetism could produce order as well as chaos. In pulsars, the universe reveals that even under conditions of unimaginable density and force, regularity can emerge. Pulsars remind us that neutron stars are not defined by a single behavior. They can be violent or calm, chaotic or precise. Plus, they can tear crusts apart with magnetic stress or mark time with unwavering rhythm. This diversity is part of what makes neutron stars so compelling. Time, rotation, and relativity. Neutron stars do not simply exist within space and time. They reshape both. Around them, the familiar flow of time slows, distances distort, and motion takes on meanings far removed from everyday experience. These effects are not theoretical abstractions. They are measurable realities, confirmed through decades of observation. Neutron stars are among the clearest places in the universe where relativity moves from equation to experience. The immense mass of a neutron star curves space-time strongly. This curvature affects everything nearby, including light and time itself. According to Einstein's theory of general relativity, the stronger the gravity, on the slower time passes. Near the surface of a neutron star, this effect becomes extreme. A clock placed there would tick noticeably more slowly than one far away in empty space. This slowing of time is not uniform. It increases as one approaches the surface. The deeper an object falls into the gravitational well of a neutron star, the more time stretches. For distant observers, processes near the star appear slowed. This gravitational time dilation has been confirmed by precise measurements of pulsar signals, whose timing reveals tiny but consistent relativistic effects. Rotation amplifies these distortions further. Many neutron stars rotate at astonishing speeds, some completing hundreds of rotations per second. At such velocities, the surface moves close to the speed of light. Special relativity becomes significant. Thus, time for matter on the surface slows not only because of gravity, but because of motion itself. Gravity and velocity combine, creating layered time effects across the star. This means that time on a neutron star is not uniform. The core, the crust, and the surface each experience time differently relative to distant observers. Even points on the surface at different latitudes experience slight variations due to rotation. Neutron stars are not only dense in matter, they are dense in relativistic effects. These distortions influence how radiation escapes the star. Light climbing away from a neutron star loses energy, becoming redshifted. Frequencies shift lower. What is emitted as high-energy radiation near the surface arrives weaker to distant observers. Correcting for this effect is essential for understanding neutron star observations. All without relativity, measurements would be misleading. Relativity also governs how matter moves around neutron stars. Orbits behave differently in strong gravitational fields. Stable orbits exist closer to neutron stars than around less compact objects. Matter spiraling inward experiences intense tidal forces and rapid acceleration. These motions generate powerful emissions, shaped by the curvature of space-time itself. In binary systems, relativistic effects become even more pronounced. When a neutron star orbits another massive object, their mutual gravity warps space-time in complex ways. Orbital paths decay slowly as energy is lost through gravitational radiation. This decay was observed in binary pulsar systems long before gravitational waves were directly detected, providing early confirmation of Einstein's predictions. One of the most remarkable consequences of relativity near neutron stars is frame dragging. As a massive, rapidly rotating object spins, it drags spacetime around with it. Near a neutron star, this effect is significant. Space itself is pulled into rotation, altering the paths of nearby matter and light. This phenomenon has been measured indirectly through precise timing of pulsars and orbital dynamics. Rotation also shapes the star's structure. Rapidly spinning neutron stars are slightly flattened at the poles, bulging at the equator. This deformation is small in absolute terms, but significant given the star's size. It influences gravitational field distribution and affects how the star emits radiation. Even tiny deviations matter under such extreme conditions, and the combination of rotation and relativity places limits on how fast a neutron star can spin. Beyond a certain speed, centrifugal forces would overcome gravity at the equator, causing matter to be flung into space. This theoretical maximum spin rate sets an upper bound observed in pulsar populations. The fact that neutron stars approach but do not exceed this limit confirms understanding of relativistic balance. Relativity also governs how neutron stars cool. Neutrinos escape from deep within the star, carrying energy away. The paths and energies of these neutrinos are influenced by space-time curvature. Cooling rates therefore depend not only on internal physics, but on relativistic effects that alter energy transport. For scientists, neutron stars are invaluable because they allow tests of relativity under conditions impossible to reproduce elsewhere. Black holes are even more extreme, but their event horizons hide information. Neutron stars remain observable. They allow measurement, comparison, and verification. They reveal how space-time behaves just before it breaks entirely. These tests are not academic. They refine understanding of gravity itself. Small discrepancies between observation and theory can point to new physics. Neutron stars therefore sit at the intersection of astrophysics and fundamental science, offering insights into the nature of reality. Relativity near neutron stars also influences how they age. As rotation slows over time, relativistic effects evolve. Timing signals change subtly. These changes provide clues about internal structure and energy loss mechanisms. By observing neutron stars across long periods, scientists watch relativity in motion. The experience of time near a neutron star is therefore layered, distorted, and dynamic. It is shaped by mass, rotation, and gravity working together. For distant observers, neutron stars appear as clocks that both keep time and bend it. This dual role, as objects within space-time and as agents that reshape it, makes neutron stars uniquely powerful. They are not passive remnants. They are active participants in the geometry of the universe. Binary neutron star systems. Most neutron stars are born alone, flung into space by the violent asymmetry of the supernova that created them. But some are not solitary remnants. Some remain bound to companions, locked into orbits that last millions or billions of years. When neutron stars exist in binary systems, their behavior changes profoundly. Gravity becomes a dialogue rather than a monologue, and the universe gains one of its most precise and revealing laboratories. Binary neutron star systems are rare, but their importance far exceeds their number. In these systems, two massive objects orbit each other at close distances, both compact enough that relativistic effects dominate their motion. Each star bends space-time strongly, and their combined influence creates an intricate gravitational environment where even small changes matter. The story of a binary neutron star system begins long before either neutron star exists. Two massive stars form together, bound by gravity from birth. They evolve in parallel into burning their fuel and shedding mass. Eventually, one star collapses into a neutron star, surviving the supernova explosion without disrupting the system. Much later, the second star follows, forming a second neutron star. If the system remains intact after both explosions, a binary neutron star is born. This survival is remarkable. Supernova explosions are violent and asymmetric, often imparting strong kicks to newly formed neutron stars. Many binary systems are torn apart at this stage. Only a small fraction remain gravitationally bound. Those that do become rare cosmic structures, shaped by precise conditions and chance. Once formed, binary neutron stars enter a long, quiet phase. They orbit each other steadily, losing energy very slowly. Their orbits are stable, predictable, and measurable with extraordinary precision. This stability allows scientists to study gravitational interactions in detail, turning these systems into natural experiments. One of the most important discoveries involving binary neutron stars came from pulsars. In some systems, one or both neutron stars emit regular pulses of radiation. By timing these pulses precisely, astronomers can track the orbital motion with incredible accuracy. Deviations as small as microseconds reveal changes in orbital shape, orientation, and energy. These observations provided the first indirect evidence for gravitational waves. According to general relativity, orbiting massive objects should lose energy by emitting ripples in space-time. This energy loss causes the orbit to shrink gradually. In binary pulsar systems, this orbital decay was measured exactly as predicted, long before detectors could observe gravitational waves directly. Neutron stars had already confirmed their existence. As time passes, binary neutron star orbits tighten. The stars spiral closer together, their orbital period shortening gradually. This process takes hundreds of millions or even billions of years. For most of their existence, binary neutron stars evolve slowly, almost imperceptibly. But gravity is patient. It never stops pulling. As the stars draw closer, relativistic effects intensify. Orbital speeds increase. Time dilation becomes more pronounced. Tidal forces grow stronger. Each star distorts the other slightly, altering shape and internal stress. These interactions reveal information about the internal structure of neutron stars, something otherwise inaccessible. Even the mutual gravity of two neutron stars also affects their rotation. Tidal interactions can synchronize spin rates or alter rotational axes. In some systems, this interaction is subtle. In others, it contributes to internal stress and energy dissipation. These processes unfold silently, detectable only through careful measurement. Binary neutron star systems also interact with their environments. If surrounding material is present, it may be accreted by one or both stars, altering mass and spin. However, many such systems are relatively clean, isolated from dense gas. This isolation simplifies analysis, making them ideal test beds for fundamental physics. One of the most profound aspects of binary neutron stars is how predictable their evolution becomes near the end. As gravitational radiation drains energy faster, the inspiral accelerates. Orbital periods shrink from hours to minutes, then seconds. In the final stages, the stars orbit each other hundreds of times per second before merging. This final inspiral phase emits gravitational waves with characteristic frequencies and amplitudes. These signals carry detailed information about the masses, spins, and internal structure of the stars. Unlike light, gravitational waves pass through matter almost unaffected, delivering information directly from the heart of the system. For decades, scientists predicted these signals mathematically. Binary neutron stars were considered ideal gravitational wave sources because their masses and sizes produce detectable frequencies. When direct detection finally occurred, it was binary neutron stars that provided some of the most detailed and informative signals. But even before detection, binary neutron stars reshaped understanding of gravity. They showed that space-time is dynamic, not static. That energy can be carried away by curvature itself. That gravity is not merely a force, but a process unfolding through time. Binary neutron star systems also highlight the long-term consequences of stellar evolution. Massive stars do not simply explode and vanish. They leave behind remnants that continue to shape the universe long after their deaths. Neutron stars preserve mass, momentum, and information about conditions at birth, carrying that history forward. In some cases, binary neutron stars include a pulsar whose beams sweep past Earth. These systems become extraordinarily valuable. The pulsar acts as a clock embedded in a relativistic orbit. Every pulse arrival time encodes information about gravitational effects, orbital motion, and space-time curvature. Through such systems, scientists have tested general relativity with unprecedented precision. Predictions about orbital decay, gravitational redshift, time dilation, and frame dragging have been confirmed repeatedly. Each confirmation strengthens confidence in the theory while narrowing space for alternatives. Binary neutron stars also reveal limits. As the stars approach merger, internal physics begins to matter more. Tidal deformation depends on how stiff or soft neutron star matter is. By observing how gravitational wave signals change near merger, scientists gain clues about the equation of state of neutron star matter, one of the great unsolved problems in physics. This makes binary neutron stars not just interesting objects, but essential ones. They connect astrophysics, nuclear physics, and relativity into a single system. They reveal how matter behaves at densities beyond laboratory reach, how gravity operates at extreme strength, and how the universe evolves dynamically. Yet for most of their lives, binary neutron stars remain quiet. They orbit in darkness, emitting no dramatic light. Their presence is known only through subtle timing signals or gravitational effects. They embody the idea that the universe's most important processes often unfold silently when neutron stars collide. For most of their existence, neutron stars are quiet. Even in pairs, their dance unfolds slowly, almost imperceptibly, over millions of years. But gravity is patient. It never loosens its grip. And when two neutron stars finally reach the end of their long spiral, the result is one of the most profound events in the universe, a neutron star collision. These collisions do not begin with chaos. They begin with precision. In the final moments before merger, the two neutron stars orbit each other hundreds of times per second. Their paths tighten into a rapid spiral, driven by the loss of energy through gravitational radiation. Space-time itself ripples outward, carrying information about mass, spin, and structure across the universe. As the stars draw closer, tidal forces intensify. Each neutron star distorts the other slightly, stretching and compressing superdense matter. These distortions are small in size but enormous in energy. They encode critical information about the internal stiffness of neutron star matter, how it resists deformation under extreme pressure. This information is embedded in the gravitational waves emitted during the final seconds. Then, in a fraction of a second, the two city-sized objects make contact. The collision is not like two solid bodies striking each other. At these densities and speeds, matter behaves in unfamiliar ways. Shock waves propagate through neutron-dense material. Temperatures spike to billions of degrees. Magnetic fields twist violently. The merged object may briefly form a hypermassive neutron star, spinning rapidly and supported by a combination of rotation and pressure. This intermediate state is unstable. It exists for milliseconds or seconds at most, depending on total mass and internal physics. The merged remnant either collapses into a black hole or settles temporarily as a massive neutron star. During this brief interval, energy is released on a staggering scale. One of the most important outcomes of neutron-star collisions is the creation of heavy elements. Under the extreme conditions of the merger, rapid neutron capture processes occur. Atomic nuclei absorb neutrons faster than they can decay, building elements heavier than iron, gold, platinum, uranium, and many others. These elements are then ejected into space, carried outward by explosive outflows. This process explains a long-standing mystery in astrophysics. For decades, scientists wondered where the universe's heaviest elements were formed. Supernovae alone could not account for observed abundances. Neutron-star mergers provided the missing source. The gold in jewelry, the platinum in electronics, and the uranium in Earth's crust owe their existence, at least in part, to these rare but powerful events. The material ejected during a merger produces a transient glow known as a kilonova. This glow fades over days or weeks, changing color as radioactive elements decay. Unlike supernovae, kilonovae are powered by nuclear decay rather than shock heating. Their light carries the fingerprints of newly formed elements, allowing astronomers to confirm theoretical predictions directly. Beyond light, neutron-star collisions are among the strongest sources of gravitational waves in the universe. The gravitational signal from a merger is distinct and rich in information. It reveals the masses of the stars, the dynamics of the collision, and clues about the behavior of matter at extreme density. These signals travel unhindered across cosmic distances, reaching detectors billions of light-years away. The first direct detection of gravitational waves from a neutron-star merger marked a turning point in astronomy. For the first time, scientists observed the same cosmic event through both gravitational waves and electromagnetic radiation. This multi-messenger observation confirmed decades of theory and opened a new way of studying the universe. Neutron-star collisions are rare on human timescales, but frequent enough on cosmic scales to shape galactic evolution. Each merger enriches surrounding space with heavy elements, contributing to the chemical diversity necessary for planet formation and life. Over billions of years, these events seed galaxies with the raw materials of complexity. The violence of a neutron-star collision is difficult to overstate, yet it is not destructive in the usual sense. While the stars themselves are transformed or destroyed, their matter is recycled into the universe. What was once locked inside city-sized remnants becomes part of interstellar clouds, future stars, and future worlds. Even after the collision, the story continues. If a black hole forms, it may be surrounded by a disk of neutron-rich debris. This disk can power jets moving at near light speed, producing brief gamma-ray bursts visible across the universe. These bursts last seconds or less, yet they rank among the most energetic events ever observed. The link between neutron-star mergers and short gamma-ray bursts was long suspected and later confirmed through observation. This connection illustrates how different cosmic phenomena, gravitational waves, gamma rays, heavy elements, are facets of the same underlying process. For scientists, neutron-star collisions are extraordinary opportunities. They compress extreme physics into observable moments. They allow tests of relativity, nuclear physics, and astrophysical modeling simultaneously. Each detected merger refines understanding and raises new questions. Yet most mergers go unseen. They occur in distant galaxies, their light too faint, their waves too weak to detect with current instruments. The universe hosts countless such events beyond our reach, shaping matter quietly and persistently. Neutron-star collisions remind us that the universe builds complexity through rare extremes. Gold is not forged gently. It is born in violence, measured not in explosions alone, but in space-time itself. shaking under the weight of collapsing matter. Gravitational waves, listening to neutron stars. For most of human history, the universe was known only through light. Stars revealed themselves through brightness, color, and motion. Even the most violent cosmic events were understood only by what they emitted across the electromagnetic spectrum. But neutron stars changed this relationship. They revealed that the universe can also be heard, not with sound, but through vibrations in space-time itself. Gravitational waves are not waves that travel through space. They are waves of space. When massive objects accelerate, especially under extreme gravity, they disturb the fabric of space-time, sending ripples outward in all directions. These ripples stretch and compress space as they pass, altering distances by minuscule amounts. For decades, these waves existed only as mathematical predictions. Neutron stars helped make them real. Binary neutron star systems are among the most powerful and precise generators of gravitational waves. As two neutron stars orbit each other, they lose energy through this radiation. The orbit shrinks. The stars spiral closer together. This slow inspiral produces a continuous gravitational signal, growing stronger and faster as the stars approach merger. Long before collision, the universe is already vibrating. What makes neutron stars especially valuable sources is their size. Unlike black holes, neutron stars have physical surfaces and internal structure. This structure influences how they deform under tidal forces as they spiral inward, as these deformations subtly alter the gravitational wave signal, encoding information about the internal composition of neutron star matter. When gravitational wave detectors first observed signals from merging neutron stars, they confirmed decades of theory in a single moment. The signals matched predictions with astonishing accuracy. The frequency increase, the final chirp, and the abrupt cutoff all reflected the physics of inspiral and collision. Space itself had carried the story across vast distances. These detections marked a turning point in astronomy. Gravitational waves offered a completely new channel of information, independent of light. They could pass through dust, gas, and even stars without obstruction. Events previously hidden from view could now be detected through space-time vibrations alone. The neutron star mergers were especially important because they combined gravitational waves with electromagnetic signals. Observatories detected light from the same event. Gamma rays, visible light, infrared emission. This multi-messenger approach allowed scientists to correlate space-time ripples with physical processes, tying abstract signals to real cosmic outcomes. The gravitational waves from neutron stars also revealed something profound about matter itself. As the stars deform under tidal stress, the stiffness of neutron-dense matter determines how much they stretch. Softer matter deforms more, stiffer matter resists. These effects leave measurable imprints in the wave signal, allowing scientists to place constraints on the equation of state of neutron star matter. This was unprecedented. For the first time, information about matter at densities greater than atomic nuclei was extracted not from theory, but from observation. Neutron stars turned gravitational waves into probes of nuclear physics, offering insight into conditions that cannot be recreated on Earth. Gravitational waves also provide precise measurements of mass and distance. Unlike light, which can be absorbed or scattered, space-time vibrations carry unambiguous information about the energy involved. From the shape of a wave signal alone, scientists can infer the masses of the neutron stars and estimate how far away the event occurred. This capability transforms neutron star mergers into cosmic rulers. They help calibrate distances across the universe, contributing to measurements of cosmic expansion. In this way, neutron stars influence understanding not only of extreme matter, but of the universe's large-scale structure. Even isolated neutron stars can produce gravitational waves under certain conditions. If a neutron star has a slight asymmetry, a tiny mountain only millimeters high, its rotation can generate continuous space-time ripples. Though weak, these signals could, in principle, be detected with sufficiently sensitive instruments. Detecting such waves would reveal internal structure and crust strength directly. The search for continuous gravitational waves from neutron stars is ongoing. It requires patience and sensitivity, far beyond current limits. Yet even the possibility highlights how deeply neutron stars connect astrophysics and fundamental physics. Gravitational waves also change how scientists think about observation itself. Instead of seeing the universe as a collection of luminous objects, it becomes a dynamic system where mass and motion leave lasting imprints in space-time. Neutron stars, compact and massive, become key voices in this cosmic symphony. The quiet power of gravitational waves mirrors the quiet nature of neutron stars themselves. These stars do not shine brightly. They do not dominate the night sky. Yet through space-time vibrations, they announce events of enormous consequence. They remind us that significance in the universe is not always loud or visible. As detectors improve, more neutron star signals will be captured. Each detection will refine understanding, narrow uncertainties, and reveal new aspects of extreme physics. The universe will continue to speak through space-time, and neutron stars will remain among its clearest messengers. Inside the core, matter no one has ever seen. At the heart of every neutron star lies a mystery that no telescope can resolve, and no experiment can reproduce. The core of a neutron star is hidden not by distance or darkness, but by physics itself. Signals from this region do not escape cleanly. Light is altered. Neutrinos carry only partial information. Gravitational waves offer hints, but not images. What exists at the center of a neutron star remains one of the most profound unknowns in modern science. The outer layers of a neutron star are relatively well understood. The crust, though extreme, follows known physical principles. Beneath it lies a region dominated by neutron-rich matter, dense but still describable using established nuclear models. But deeper still, pressure rises beyond any regime tested by experiment. At these depths, uncertainty dissolves. The core exists under conditions so extreme that ordinary distinctions between particles may no longer apply. Neutrons are packed together so tightly that their individual identities begin to blur. The strong nuclear force which binds atomic nuclei becomes a dominant player. Gravity presses inward relentlessly, while quantum mechanics resists compression at the smallest scales. The result is a balance unlike anything else in the universe. One possibility is that the core is composed of superfluid neutrons. In this state, neutrons flow without friction, behaving as a single quantum entity on macroscopic scales. Superfluidity is observed in laboratory conditions at extremely low temperatures, but in neutron stars it may occur at immense densities instead. If true, and this would allow angular momentum to be stored and transferred in unexpected ways, explaining sudden changes in rotation observed in pulsars. Another possibility is that the core contains exotic particles rarely seen elsewhere. Hyperons, particles containing strange quarks, may appear when pressure forces matter into new configurations. These particles would alter the star's internal pressure balance, influencing stability and maximum mass. Their presence could explain why some neutron stars collapse into black holes, while others do not. More extreme theories suggest that at sufficient pressure, neutrons themselves dissolve. Their constituent quarks, up and down quarks, may roam freely, forming a quark-gluon plasma, or a state known as quark matter. In such a core, a matter would exist in a form not seen since the earliest moments after the Big Bang. A neutron star with such a core would not truly be a neutron star at all, but something more exotic. These possibilities are not mutually exclusive. A neutron star may contain layered phases of matter, transitioning from neutron-rich material near the crust to exotic states at the center. The exact structure depends on how matter behaves at densities far beyond nuclear limits, a question that remains unresolved. The challenge in understanding neutron star cores lies in the equation of state, the relationship between pressure, density, and temperature inside the star. Small changes in this relationship lead to large differences in predicted size, mass, and stability. Without direct access, scientists rely on observation to constrain these possibilities. A mass and radius measurements offer clues. A stiffer equation of state produces larger neutron stars for a given mass. A softer one yields smaller, denser stars. Observations of massive neutron stars challenge models that predict early collapse, ruling out certain exotic core compositions. Yet no single model fits all data perfectly. Rotation adds another layer of complexity. Rapidly spinning neutron stars experience centrifugal support that slightly counteracts gravity. This affects internal pressure distribution and may stabilize otherwise unstable configurations. Understanding these effects requires combining nuclear physics, relativity, and fluid dynamics into a single framework, a task that pushes theory to its limits. The core also influences how neutron stars cool. All neutrino emission processes depend sensitively on internal composition. Some reactions cool the star rapidly, others slow the process. Observed temperature changes over time, therefore provide indirect evidence about what may exist at the center. Yet interpretations remain uncertain, as multiple models can explain the same data. What makes the mystery of neutron star cores especially compelling is that it connects the smallest scales of physics to the largest. Quarks, nuclear forces, and quantum states determine the fate of objects visible across the galaxy. Neutron stars compress subatomic physics into astronomical consequences. Despite uncertainty, progress continues. Each gravitational wave detection, each precise pulsar measurement, and each improved simulation narrows the range of possibilities. The mystery does not shrink quickly, but it does sharpen. Scientists are learning not what must exist, but what cannot. The core of a neutron star represents a boundary of knowledge. Beyond it, current theories may fail. New physics may emerge. Understanding this region could reveal insights not only about stars, but about the fundamental structure of matter itself. Neutron stars therefore serve as messengers from a regime unreachable by experiment. They challenge assumptions, test theories, and remind us that the universe still contains conditions we barely comprehend. The thin line between neutron star and black hole. Neutron stars exist at a boundary so precise that crossing it changes the nature of reality itself. They are not simply dense objects. They are survivors, remnants that resisted total collapse by the narrowest possible margin. Add too much mass, you disturb the balance too far, and the neutron star ceases to exist as such. Gravity completes its final victory, and a black hole is born. This boundary is not marked by a visible line in space. It is defined by physics, by the limits of pressure and resistance. Inside a neutron star, gravity presses inward with relentless force. What prevents total collapse is not structure or energy production, but the quantum mechanical behavior of matter under extreme compression. neutron degeneracy pressure and nuclear forces push back, holding gravity in check. But they can do so only up to a point. That point is known as the maximum neutron star mass. Beyond it, no known force can prevent further collapse. Determining this limit is one of the most important challenges in astrophysics, because it reveals how matter behaves at the highest possible densities before space-time itself gives way. Observations show that neutron stars can have masses more than twice that of the Sun. This alone rules out many theoretical models of neutron star interiors. If matter were too soft, too easily compressed, such massive neutron stars could not exist. The fact that they do exist tells scientists that neutron star matter is surprisingly stiff, resisting compression more strongly than some theories predicted. Yet even this stiffness has limits. As mass increases, pressure must rise faster than gravity. Eventually, gravity wins. When that happens, the neutron star collapses inward. Unlike supernova collapse, this transition may occur quietly. Without a dramatic explosion, the star's surface disappears behind an event horizon, and the neutron star becomes a black hole. This transformation is irreversible. A black hole has no surface, no crust, no magnetic poles in the traditional sense. Information about the neutron star's interior is hidden behind the event horizon. The universe draws a curtain, and the object that once resisted gravity vanishes from view. The thinness of this boundary is striking. A neutron star only slightly more massive than another may collapse, while its lighter counterpart survives for billions of years. This sensitivity highlights how finely balanced neutron stars truly are. They are not robust objects in the ordinary sense. They are precise outcomes of competing forces. Mass transfer can push a neutron star across this boundary. In binary systems, neutron stars may accrete matter from companions. As mass accumulates, the internal pressure rises. For a long time, the star adapts. But if accretion continues unchecked, the limit is reached. Collapse follows. Neutron star mergers also test this boundary directly. When two neutron stars collide, the combined mass often exceeds the stability threshold. The merged object may survive briefly as a hypermassive neutron star, supported by rapid rotation and thermal pressure. But this support is temporary. As rotation slows and heat dissipates, collapse becomes inevitable. A black hole forms at the center of the wreckage. This fleeting existence offers a final glimpse of neutron star matter under extreme stress. For milliseconds, matter exists in a state more massive than any stable neutron star, yet not yet a black hole. Observing these moments through gravitational waves and electromagnetic signals provides rare insight into the transition between two of the universe's most extreme objects. The question of how neutron stars fail is as important as how they survive. It reveals the limits of quantum mechanics under gravity. It tests whether new states of matter can exist or whether known forces suffice. Each observed massive neutron star pushes the boundary outward, challenging theory. Each collapse confirms that the boundary exists. The distinction between neutron star and black hole is not merely academic. It shapes the population of compact objects in galaxies. It determines how much matter is locked away behind event horizons versus recycled into space. It influences the types of signals astronomers observe, from pulsars to gamma ray bursts. Neutron stars therefore occupy a transitional role in cosmic evolution. They are not endpoints in the way black holes are. They are holding patterns, pauses where matter resists gravity for a time. Some last billions of years. Others exist briefly before collapsing. All exist under constant threat from the force that created them. This precarious existence gives neutron stars a sense of tension. They are stable, yet never entirely safe. Their survival depends on mass, rotation, composition, and environment. Change any one of these, and the balance may tip. Understanding where this boundary lies also has implications beyond astrophysics. It informs nuclear physics, quantum mechanics, and theories of gravity. It tests whether current models remain valid under the most extreme conditions known. Neutron stars are not just cosmic curiosities. They are stress tests for the laws of nature. Neutron stars as cosmic laboratories. Neutron stars are not studied simply because they are rare or extreme. They are studied because they offer something no laboratory on Earth ever could. They place matter, gravity, and energy into conditions so intense that the fundamental laws of physics are tested continuously. In doing so, neutron stars become natural laboratories, experiments conducted by the universe itself, running for millions or billions of years. On Earth, experiments are limited by scale. Pressure chambers, particle accelerators, and fusion reactors can only approach certain thresholds before materials fail or energy demands become impossible. Neutron stars bypass these limitations entirely. They compress solar masses of matter into volumes small enough to fit inside cities. They sustain gravitational fields strong enough to bend time and space. They do so without human intervention, obeying the same laws scientists seek to understand. One of the most valuable aspects of neutron stars is their ability to probe nuclear physics. Inside their cores, matter exists at densities greater than those found inside atomic nuclei. Under such conditions, the behavior of particles is uncertain. The forces that bind protons and neutrons together may behave differently. New particles may appear. Old assumptions may fail. Neutron stars allow scientists to test these possibilities indirectly through observation. Mass and radius measurements are key tools in this effort. By determining how massive a neutron star is and how large it appears, scientists can infer how compressible its interior must be. A star that is both massive and relatively large suggests stiff matter that resists compression. A smaller star of similar mass suggests softer matter. Each observation rules out entire classes of theoretical models. Rotation provides another probe. Rapidly spinning neutron stars experience strong centrifugal forces that compete with gravity. The maximum observed spin rates place limits on how rigid neutron star matter must be to avoid breaking apart. These constraints feed directly into theories of dense matter, narrowing the range of possible behaviors. Cooling behavior also serves as a diagnostic. Neutron stars cool primarily through neutrino emission from their interiors. The rate at which they lose heat depends on internal composition and particle interactions. By observing surface temperatures over time, AUGA scientists infer what processes dominate inside. Differences between stars hint at differences in internal structure. Magnetic fields add further complexity. Extreme magnetism affects particle interactions, crust behavior, and energy transport. In magnetars, magnetic energy release dominates emission. Studying these objects helps scientists understand how magnetic fields behave under conditions far beyond terrestrial experience. Neutron stars also serve as laboratories for gravity itself. Their compactness makes relativistic effects unavoidable. Time dilation, frame dragging, and space-time curvature are all measurable near neutron stars. Observations of pulsar timing and binary motion have confirmed predictions of general relativity with remarkable precision. In some cases, neutron stars push these tests into new territory. Binary systems allow measurement of gravitational radiation, orbital decay, and relativistic precession. Each system acts as a unique experiment, probing gravity under slightly different conditions. Together, they build a comprehensive picture of how space-time behaves under extreme mass and motion. The laboratory role of neutron stars extends beyond known physics. They may also hint at new phenomena. Some theories predict that exotic states of matter or unknown particles could exist in neutron star cores. Others suggest modifications to gravity under extreme conditions. Neutron stars provide the only accessible environment where such ideas can be confronted with reality. Importantly, neutron stars offer these insights without requiring control. Unlike laboratory experiments, scientists cannot adjust parameters at will. They must observe, interpret, and infer. This limitation demands careful analysis and humility. Conclusions are drawn cautiously, supported by multiple lines of evidence. This observational approach has strengths. Nature explores combinations of conditions humans might never consider. Neutron stars come in a range of masses, spins, magnetic field strengths, and environments. Each variation reveals different aspects of physics. The diversity of neutron stars enriches the laboratory. Neutron stars also connect microscopic physics with macroscopic consequences. The behavior of quarks and neutrons influences the stability of objects visible across the galaxy. This link between the smallest scales and the largest is one of the most compelling aspects of astrophysics. Neutron stars make this connection tangible. The laboratory role of neutron stars also evolves with technology. Advances in telescopes, detectors, and computational models continuously improve observational precision. Gravitational wave detectors add a new dimension, allowing direct measurement of extreme events. Each technological step opens new windows into neutron star physics. Yet, even with these tools, limitations remain. Many neutron stars are too distant, too faint, or too isolated to study in detail. Observations provide snapshots rather than full histories. Models must fill gaps, guided by data but constrained by uncertainty. The laboratory is vast, but access is partial. Despite these challenges, neutron stars remain among the most informative objects in the universe. They compress fundamental physics into observable form. They test theories under conditions unattainable elsewhere. They remind scientists that understanding the universe requires both imagination and restraint. What we still don't understand. Despite decades of observation and theory, neutron stars remain incomplete stories. They are among the most studied objects in astrophysics, yet some of their most fundamental properties remain uncertain. This uncertainty is not a failure of science. It is a reflection of how extreme these objects truly are. Neutron stars exist at the edge of what can be known. One of the central unknowns is the exact nature of matter inside neutron stars. While models describe crusts, superfluid layers, and dense cores, no observation has yet confirmed the precise composition. Competing theories predict different particle populations, different phases of matter, and different internal dynamics. Observational data narrows possibilities, but it does not select a single answer. The equation of state of neutron star matter remains unresolved. This equation governs how matter responds to pressure at extreme density. Small differences in the equation lead to significant differences in predicted size, mass, and stability. Despite advances in gravitational wave astronomy and pulsar timing, uncertainty remains. The universe has not yet revealed its full answer. Magnetic field evolution is another mystery. Scientists know how neutron stars are born with strong fields, but how these fields evolve over millions of years is less clear. Some neutron stars retain strong fields far longer than expected. Others decay rapidly. The internal mechanisms driving these changes are not fully understood, and the origin of magnetars, while partially explained, still raises questions. Why do only some neutron stars develop such extreme magnetic fields? What initial conditions are required? Are magnetars fundamentally different at birth, or do they evolve differently after formation? These questions remain open. Rotation behavior also holds surprises. Pulsar glitches reveal sudden transfers of angular momentum between internal components. These events suggest complex internal dynamics involving superfluid layers and crust coupling. Yet models struggle to reproduce the full range of observed behavior. Each glitch offers a clue, but no complete explanation. Neutron star cooling presents further uncertainty. Some neutron stars cool faster than models predict. Others retain heat longer. These differences imply variations in internal composition or neutrino emission processes. Disentangling these effects requires long-term observation and careful interpretation. Binary interactions introduce additional complexity. Mass transfer, tidal forces, and magnetic interactions can alter neutron star evolution in ways that are difficult to model precisely. Observations capture outcomes, but not always processes. Even gravitational wave observations, as powerful as they are, leave gaps. Signals encode information about tidal deformation and mass, but extracting detailed interior properties remains challenging. Future detections will help, but fundamental limits may remain. Perhaps the most profound unknown is how neutron stars connect to black holes. Where exactly does one end and the other begin? Is there a sharp boundary, or a smooth transition? Do exotic intermediate states exist? Observations suggest a mass gap, but its origin remains debated. These unanswered questions do not diminish the importance of neutron stars. They enhance it. Each mystery points to physics under conditions never replicated on Earth. Neutron stars remind scientists that understanding is a process, not a destination, hidden in plain sight. Why neutron stars are hard to find. Neutron stars are among the most extreme objects in the universe, yet most of them remain invisible. This seems contradictory. How can something so dense, so powerful, and so influential remain hidden across the vastness of space? The answer lies not in their importance, but in their subtlety. Neutron stars do not announce themselves loudly. They reveal their presence only under specific conditions, and when those conditions are absent, they fade into cosmic silence. Unlike ordinary stars, neutron stars do not shine through sustained nuclear fusion. They produce no steady light fueled by internal reactions. Instead, any radiation they emit comes from residual heat, magnetic activity, or interactions with their environment. As they age, they cool. As they cool, they grow dimmer. Over time, many neutron stars become effectively invisible against the background of space. Size also works against detection. Neutron stars are incredibly small on astronomical scales. Even relatively nearby neutron stars can escape detection because their surface area is tiny. A neutron star may be hotter than a planet, but its total light output can be lower simply because there is so little surface from which light can escape. A distance quickly overwhelms visibility. Orientation plays a crucial role as well. Pulsars are only observed if their emission beams cross Earth. Most neutron stars do not have beams aligned in our direction. Their radiation sweeps harmlessly through empty space. From Earth's perspective, these stars do not pulse. They do not signal their existence. They rotate silently. Magnetic field strength also determines detectability. Neutron stars with weaker magnetic fields emit less radiation. Without strong magnetism to accelerate particles or channel emissions, these stars remain quiet. They cool, spin down, and fade into obscurity. Over time, the galaxy accumulates a hidden population of such remnants. Environment matters. Neutron stars embedded in dense regions, such as supernova remnants or binary systems, are easier to find. While interactions with surrounding matter produce radiation that betrays their presence. Isolated neutron stars drifting through sparse regions of space may go undetected for billions of years. Even when neutron stars emit radiation, it may not be in wavelengths easily observed. Some emit primarily in X-rays or gamma rays, requiring specialized instruments. Others emit faint radio signals lost amid cosmic noise. Detection depends on technology, timing, and luck. Motion adds another challenge. Neutron stars are often born with high velocities due to asymmetric supernova explosions. They can travel rapidly through the galaxy, moving far from their birthplaces. Over millions of years, they disperse, becoming difficult to associate with any visible structure. A neutron star may pass near Earth unnoticed, its presence detectable only through subtle gravitational effects. Estimates suggest that the Milky Way contains hundreds of millions of neutron stars, yet only a small fraction have been detected. The rest form a hidden population, silent witnesses to ancient supernovae. They drift through space, unseen and uncounted. This invisibility shapes our understanding of the universe. Observations represent a biased sample favoring the loudest and most active neutron stars. Quiet ones remain unstudied, leaving gaps in knowledge. Recognizing this bias is essential. The universe contains far more than what can be seen. Efforts to uncover these hidden stars continue. Surveys search for faint X-ray sources, subtle gravitational effects, and rare interactions with interstellar matter. Each discovery expands the known population, but the unseen majority remains. Neutron stars remind us that the universe is not defined by what is obvious. Some of its most important components operate quietly, shaping cosmic evolution without spectacle. Their silence is not emptiness, it is persistence. As this documentary approaches its conclusion, attention will shift from what neutron stars hide to what they give back to the universe. Though many remain unseen, their influence extends far beyond their small size and quiet nature.